Hello and welcome to the course Design Borefields with Confidence. This is the third chapter of the second part, where we'll be taking a look at the borefield physics for our first time, and namely at the short-term effects. Because last chapter we talked about hourly and monthly temperature profiles, what we can see on them, what we can learn from them without actually simulating something. Now, today we will be looking at what's behind these profiles. And what causes them, what's the physics that give rise to the different temperatures and the short and the long-term behavior. And this is the profile we talked about last time, and we said, well, we basically see two different things here. We have some seasonal and some yearly variation. Temperatures go up and down, and over the years they go down due to the imbalance. It's a long-term behavior. And on the short term, we have our peak powers, our fluid temperatures that are related to, but not equal to, the borehole wall temperature. And it's these fluid temperatures we're actually interested in because we're designing our borefield to stay within these certain temperature limits. And that's how we can look at this thermal behavior. We can look at it from the short term in the order of hours, which is the content of this chapter, and on the long term, in the order of years or also seasons, which will be covered in the next chapter. Now, in order to understand further this difference between the long and the short term, let us take a look at our first equation of this course, stating that our average fluid temperature, Tf, and the bar on top indicates that's an average temperature, it is equal to our borehole wall temperature. There everything starts, plus or minus a certain delta T. And so, as said, if we are cooling or we are injecting heat into the ground, our fluid temperature is warmer than our borehole wall temperature. So we have a positive delta T. But if we are extracting heat from the ground, our fluid temperature will be colder than the borehole wall temperature, meaning that in this case we have a negative delta T. Now, this temperature difference between the fluid and the borehole wall temperature is equal to the specific heat exchange, the power per meter borehole, which is Q with a dot T, multiplied by the effective borehole thermal resistance, which will be the star of today's video. Now, before we jump into that, let us take a quick side route to the electricity domain, where you perhaps recall the law of Ohm stating that the voltage across a certain electrical component is equal to the resistance, Ohm of that component multiplied by the current. So the higher the current, the more voltage drop, the higher the resistance, also the higher voltage across your components. Now in the domain of heat transfer, you can do the same. So our delta T, the difference between two temperatures, basically is equal to the same resistance, but now it's an effective borehole thermal resistance multiplied by the power, which in this case is a thermal power. And if we take a closer look at, well, what is this equation now? We see here that our thermal resistance, or RB star, it's basically all the different steps or all the different layers that can pose a risk or a resistance for the heat to travel from the fluid to the borehole wall. So if we take a look at this, the heat is in the fluids and it needs to go to the borehole wall. So first it needs to pass from our fluid to our pipe, which is a convective heat transfer. It's from a fluid to a solid, so it's convective. Then it needs to pass through the pipe, and then from the pipe through the grouting material to the borehole wall. And these three different resistances make up the effective borehole thermal resistance. Now, it also states that it's simplified. Over on the textbook on our website, you can see a more scientifically correct way of looking at this, but from a physics point of view, from just looking at the insides, this will be enough. So if we then take a second time at our equation, at this very instance. So we have a certain borehole wall temperature, if we are extracting now 10 kilowatts from the ground, our borehole wall temperature will not change in the matter of hours. So that's why we can actually differentiate between short and long term. When we're just talking about powers, we can assume that the borehole wall temperature is constant and that it's just the fluid temperature who varies. Over the years, of course, we have, being energy extracted or injected into the ground, the borehole wall temperature will change. But that's more, due to the energy. So it's an energy-related problem. So that's why we can make a differentiation there. So let us now take a closer look at this short-term effect, this second term in the equation. Now, the first part of this Qt RB star is exactly this Qt. It's the power per meter extracted from our borefluid. And if we want to keep our fluid temperatures as close as possible to our borehole wall temperatures, it is good to have, a very small specific heat exchange, a specific power per meter heat extraction or injection. So what is important here is the total borehole length. Imagine you have, again, 10 kilowatts that you want to extract from your borehole, and you have only one borehole of 100 meters deep. Then we know that the stress on each meter of borehole will be 100 watts per meter of heat extraction. Now, if you have the same heat extraction, the same 10 kilowatts for two boreholes of 100 meter, the stress on each meter will only be 50 watts. So in the second case, our Qt will be half. So also our fluid temperatures will be way closer to our borehole wall temperature. So basically, for the short term, our configuration does not matter. Whether these boreholes are long or short or whatever, we just care about how many borehole meters is there to divide the power with. So this brings us to a little bit of a contradiction, because you can say that if you are designing a bore field, you actually want to have a bore field that is as small as possible because you want to have it economically viable. But if we look at this Qt, if you want a smaller bore field, so we want our fluid temperatures to be as close to the borehole wall temperature as possible, we need more borehole meters. Because more borehole meters means that this Qt will be smaller, meaning that our delta T will be smaller, and that also our fluid will be close to the borehole wall temperature. So that's a little bit of a contradiction there. Making the bore field larger will make this Qt smaller and will bring the fluid temperature closer to the borehole wall temperature. So it's just important that you know that this is a really important aspect, just the amount of meters you have. But the second thing that comes to our rescue is exactly this borehole thermal resistance, this R star B. And as said, this can consist of different resistances, and of each of these resistances, you as a bore field designer have an influence on. So depending on the choices you make, you can make this resistance larger, which is not what you want, or you can make it smaller, again, bringing the fluid temperatures closer to the borehole wall temperature. And the first resistance was this convective fluid resistance. Now, in order to understand this, we need a little bit of fluid mechanics. And on the slide, you can see here clearly what is important. So, fluid can be in different regimes, what we call. So imagine you're at home and you're opening the tap, your water tap in the sink, just ever so slightly. What will happen is you will get a very clean stream of water going down. And you can imagine all the droplets are beautifully next to each other. They move parallel. And it's what we call a laminar flow rate. It's very well behaved. However, if you turn the tap open all the way, you get a very turbulent behavior. The water comes just rushing down, all the droplets mix to each other. It's a very turbulent behavior. If you, for example, also look at the clouds, it's also very turbulent. It's going all over the place. And when we think about heat transfer, if we have a pipe where all the water is beautifully laminar, or fluid is beautifully laminar, the droplets in the middle that also carries some heat, yeah, they never touch the borehole wall. So it's really hard to transfer heat in this sense, because the heat needs to travel to all these different layers before it can reach actually the borehole wall. Whereas in the turbulent behavior, if we have a higher flow rate, yeah, our droplets are mixing, and every droplet that contains a certain amount of thermal energy will touch the borehole wall at one time or another, so it's easier to transfer heat. So for the fluid resistance, we typically want a turbulent behavior. For a hydraulic resistance, as you will discuss in a couple of parts further on, that is not what we want. So it will be an interesting trade-off in the future. But now we want typically turbulent behavior. But the question is, well, if this is of such importance, when is the fluid laminar and when will it be turbulent, and what's this transition zone? And therefore we need to understand the Reynolds number. Now, the Reynolds number is a very famous number in the domain of fluid mechanics because it tells us exactly when we're laminar and when we're turbulent. And it consists of 4 different elements. So it's a non-dimensional number, meaning it has no units. And it takes into account the fluid density, your pipe diameter, the fluid velocity, meters per second, so not the flow rate, but the velocity of the fluid in your pipe, and the dynamic viscosity of your fluid. And if you take all these things into account, and we will see they can vary over time, but that's not important at the moment. If you take all these 4 parameters, you can calculate the Reynolds number. And if it's below 2300, then it's laminar. If it's above 4000, then it's turbulent. And then lately, scientists have discovered there is some transient layer in between. So we know that after 2300, turbulence starts, typically. And we know that at 4000, we'll definitely be turbulent. So somewhere in between, we can say it's a combination of both. And in GHE2, we use, therefore, a linear correlation. Now, just to illustrate the importance of the Reynolds number on our total borehole resistance, we have this graph where you have the Reynolds number ranging from 2000 to 6000, and we have a borehole resistance on the vertical axis. Now what you can clearly see here is this 2300 threshold. So the stars, or the plus signs, are the simulations in GHE2. We see in laminar it's more or less constant. Later on we will see that there is also some variation there, but it's more or less constant. And then after 2300 it drops down significantly. Now in Earth Energy Designer, which is an older software, you see that this transition zone is not yet taken into account. So there it's an unphysical jump between the laminar flow and then immediately after the turbulent flow. And you can see that with the more nuanced models, there is indeed a sudden jump, but it's going down exponentially, let's say, and after 4000 it converges. So the fluid regime is really, really important. The next part is the pipe resistance, and here you typically don't have much of an influence of. It depends on the material properties of your pipe, which typically is plastic, and depending on your wall thickness, which is related to the pressure rating of your pipe, it is what it is. If you drill deeper, you typically need a bigger wall, a higher wall thickness to withstand the hydraulic pressure in your pipes, and your pipe resistance will be bigger. Now, there are also commercial solutions to overcome this. For example, Haka has developed some conical probes called the gerotherm vario and flux probes, where they say, well, you only need this high pressure rating at the bottom of your borehole. So they make their wall thickness conical so that at the critical point, you have the critical wall thickness, the big wall thickness, but at the top, you have a smaller wall thickness. Now, they do that to minimize the hydraulic losses, the pressure drop, which we will discover later. But this also has the side benefit that on average, your wall thickness is smaller, so also your pipe resistance is smaller. Now, another solution is from Janssen, it's called a high press probe. And here they say, well, okay, for these deep boreholes, instead of having a thick plastic wall, what we're going to do is we're going to install a metal layer in our probe, which is way stronger, so we can make our wall thickness again somewhat smaller. And the advantage of this metal is that it also conducts heat better. So here is also a solution, if you opt for it, that you can change the pipe resistance. But typically it's, if you just go for regular probes, it's plastic and it has a material thermal conductivity of around 0.4 watts per meter Kelvin. Now the third resistance is the grout resistance. So we're now in the pipe and we need to go to the borehole wall. So we need to go through the grout. And what is important here is, where are our pipes in the borehole? Now this is of course a very theoretical thing, because they go down and you can't actually see where they're going. Now you have the concept of these spaces you place between them in order to keep them separate as possible. But in the end, it's not very practical to do so, because if you install them, instead of letting the pipe go down very fast in order to prevent the borehole from collapsing, you need to stop every few meters, install it, tape it, and let it go down. So that in the end, when you measure it, it does not make that much of a difference. So, but what you can see here, if you were able, one way or another, to keep the pipes surely to the sides of the borehole, that your borehole resistance will be indeed lower. Typically what I do and suggest is that, since you don't know where they will be, is just assume that they will be at half the radius, which is basically the green situation here. Now a second thing where you actually have influence on is your grout thermal conductivity. Now, depending on which material you choose, whether it's bentonite or silica or whatever, you can have a conductivity between 0.6 watt per meter Kelvin or 2.5 watt per meter Kelvin for really thermally enhanced grouts. And this of course has an effect, because the better the conductivity of your grout, the easier it is for your heat to pass through it, and the lower your resistance will be. Now there is another important element related to the grout. You can't pump it up forever, because in the end you need to get it down into your borehole. And therefore you need to have a pumpability of your fluids, the ability of your material, your grout, to be pumped down there. So always contact your driller to see what is feasible there. Also, on another note, not all boreholes are grouted. For example, in Scandinavia, where they drill the boreholes into solid rock, they typically just fill it with groundwater and install the probes in it. Now, here it's way more difficult to actually know what your conductivity will be, because the water can also move up and down, and you have also convective effects. And we've written a couple of sentences over on our website in the textbook to explain a little bit how that works. Now, a last thing where you as a designer have an influence on is whether you go for a single or W tube, or also a coaxial, or some special solutions like separatus, for example. But typically the discussion between a single or W tube is one of the most common and the most heated debates in the domain of borefield physics and borefield design in general. Now, we have on our knowledge base already a couple of articles covering this. We will also cover it later on in this course. But in general, all things considered and all other things being equal, having a W tube is better thermally than a single U tube. Because, this amount of surface area is twice as big, meaning that it's easier to transfer the heat to the borehole wall. Now, the very important side note is here that if you go from a single to a double tube, your fluid velocity or your flow rate per probe will be different. Because instead of going pumping it through one pipe, you're now pumping it to two pipes. So each pipe only gets halves, meaning that, if you recall, our fluid resistance can also change significantly. So just for the grout resistance, yes, it's definitely better. For your effective borehole thermal resistance, it really depends. And we will be covering that in much more detail later on. So let's summarize. We need our effective borehole thermal resistance to go from our borehole wall temperature to our fluid temperature. And we typically want to have it as small as possible. It ranges between 0.05 meter Kelvin per watt and 0.25 meter Kelvin per watt. And it's basically a power problem. So our ground temperature at these short terms is more or less constant. And what can we do to influence or make this power problem or solve this power problem is to change the fluid regime, laminar turbulence. We can have an influence on the pipe to the borehole center, although it's hard. But for example, if you drill a smaller borehole, your pipes will on average also be smaller closer to the walls. You can change your grout thermal conductivity, and we had this strange effect of the borehole length. So our total borehole length is a really, really important aspect as well to this power problem. So not the configuration, just how many borehole meters is there, how many meters of heat exchanger. Now, this was the power problem. This was the short-term effect. In the next chapter, we will be taking a look at what the seasonal variation comes from and how the long-term effect or the influence of the imbalances is actually taken into account in the temperature profiles. So I'm seeing you in the next chapter.